Welcome Geos406 students. This is your last homework module. So you're almost finished with these homework modules. This one is all calculations based, and it's going to give you a little hands-on practice using volume change and pressure relationships in a magma chamber to estimate surface deformation or displacements of hypothetical GPS stations around your volcano. So this is a great volcanological monitoring tool. It's used really readily at volcanoes around the world because surface displacements around a volcano that can be measured accurately using satellites, GPS, tilt meters, synthetic aperture radar. Those signals can tell us a lot about how magma is moving and how it's stored underneath the crust and whether the volcano is filling up with new magma getting ready to erupt soon. Okay, so what is surface deformation? There's a cartoon I have on the right, and this is a really nice illustration. So basically what happens is when you have a volcano that's filling up with new magma, the volume of the magma reservoir basically increases. You can think of this very simplistically like blowing up an elastic balloon. You put air into the balloon, and the surface of that balloon expands outward as the volume changes. So in stage one here in this cartoon, you have some tilt meters, you have GPS stations, magma in the reservoir fills up, the reservoir begins to swell, the crust around it is, well, we assume it's elastic, kind of like the balloon analogy, and inflation begins. So this means that the volcano at stage two, the surface of that volcano is going to actually move and it's going to be displaced. So as the magma chamber inflates, the ground above it swells, and you can measure that change using tilt meters. That'll be, the tilt increases as the area around the vent of the volcano moves up. The GPS stations will move up and away from the center of the volcano as the magma reservoir increases in volume and pressure. At stage three, if your volcano then erupts and gets rid of the excess volume and pressure that was inside of the magma reservoir, the reservoir basically shrinks back down into a shape that's much smaller, and that means that the ground surface will basically return back to a state that is deflated from what it was when inflation was at its peak. So the ground surface subsides, and the GPS stations around that volcano will move down and inward back towards the center of the vent. So this is a really important geophysical monitoring signal because deformation that's radial around a volcano that we know is an active volcano and shows signs of unrest is a really strong indication that there's magma intruding into the crust in the magma reservoir. And if you get enough of a magma volume intruding into the reservoir, you can trigger an eruption. Okay, so what is the magnitude of surface deformation? Well, it can be pretty extreme. So the example from Mount St. Helens just before the May 18th, 1980 eruption was extreme. There was a cryptodome, which basically is just magma that rises up underneath the surface and it doesn't make its way out. So you have magma shallow underneath the flanks of the volcano. In this case, it intruded into the north flank of Mount St. Helens, causing a giant bulge. The bulge was growing at a rate of 1.5 to 2 meters per day. That's a lot. Most volcanoes don't deform this much. Some can deform a lot, like Okmok will deform, tens of centimeters over years before an eruption. Quite measurable. More typical, volcanoes will deform on the order of millimeters to centimeters. It really depends a lot upon the volcano, the state of the crust, how much magma is intruding, how deep that magma is, and some other things. So an example on the right from the USGS is from 2 periods of time at Kilauea volcano, 1998 to 99 and 99 to 2001. So in this case, the volcano was subsiding. So magma was withdrawing from underneath the central crater in Kilauea caldera, and you can see if we start at time 0, centimeters per year of deflation. From distance outward along the volcano, you can see that subsidence is, on the order of 6 centimeters, and then comes back up again when the volcano refills with magma. And there's the bulge. All right, so how do we measure volcano deformation? There's a whole field of study called geodesy, and geodesy was not originally developed for this purpose. Geodesy was a way to measure the geoid, which is a gravitational reference frame surrounding the Earth, and it's basically, you can use it for a lot of different things. So one great application of this is measuring surface changes around volcanoes. Terrestrial or ground-based methods include a lot of different things. You can use leveling and tilt meters. You can use electronic distance measurements, basically surveying, very accurate surveying. You can use GPS. That's a very common one that we use in Alaska because you can do this remotely. And there's also some satellite methods, interferometric synthetic aperture radar. So I'm not going to go into great detail about how each of these methods work. That's a little beyond the scope of just one lecture. So if you want some more information or you want to know who's doing this type of research, just reach out to me by email and I'll help you along there. So tilt is a really great one. We don't use it a lot in Alaska, but we do have a few remotely operated tilt meters around some of our volcanoes. Tilt is basically just a really fancy level placed on the side of a volcano, and you can measure deformation or surface displacement based upon how much tilt you can observe with time. So Hekla volcano in Iceland had a pre-eruptive inflation event followed by a co-eruptive subsidence for the last couple eruptions, a couple eruptions in the 1985 to 2005 timeframe. So the way this works is when the tilt goes up, that means you're inflating. That means magma's filling up inside of the volcano. When there's an eruption, you get rid of that magma, so the surface of the volcano sinks back down again because you've gotten rid of that volume change underneath the ground. So that's the deflation. And then magma fills up again, and the tilt meter shows that the elevation is rising. You erupt, you get rid of that magma, and it goes back down again, and then you repeat. INSAR is really great. This is a way you can use radar bouncing off the ground surface in different times and different angles to show differences in the amount of radar scattering coming back from the ground, which is linked with the ground surface elevation. The Galapagos Island actually shows some really interesting INSAR patterns between 1992 and 1999. So down on this right-hand inset, you can see a bunch of colored bullseyes here. Basically, these are the way you process the INSAR data to retrieve ground motion. So when you have a ringed pattern like that, you can see that there's uplift happening at the volcano that's centered around the center of the caldera here. So that's what this bullseye means right here. All right, so we're going to apply something called the MOGI model, which is a very nice, basic, simple, but often quite accurate model that describes how volcanoes deform when their magma chambers in the crust fill up with magma. There are some assumptions that go into this that aren't always accurate. So it's important to know something about the geometry of your volcano and the geometry of its magma storage and plumbing system. So this model was developed by Kiyu Mogi, and I actually linked into the bottom of the slide here a link to his 1958 paper. If you want to read more about the Mogi model from that paper, you can do so. So he investigated patterns of surface deformation associated with Sakurajima and Kilauea, and using a theory of elasticity, which basically means that you assume the ground and the crust of the earth is elastic. You can kind of basically call it a balloon, an elastic balloon, or a balloon with an elastic shell. Mogi suggested surface deformation measured before and after eruptive activity could be fit by a spherical pressure source buried in this elastic crustal medium. So in this model, changes in volume and pressure within a magma chamber of a radius, which here is noted as A, and depth D, can cause vertical U sub Z and horizontal U sub R displacements at the surface, radially around the center, the epicenter on the ground surface above your magma chamber. So that would be basically the vent of the volcano. So the magnitude of the displacements changes with radial distance away from the center. So this model is valid only when the depth to your magma reservoir is much greater than the radius of the magma chamber. So if you have a really shallow, really, really big magma chamber, the MOGI model breaks down. Okay, so now we can use this to solve a problem. We can solve a problem between pressure and volume change in a magma chamber and surface deformation. And there's a lot of different things you can do with this. You can figure out how deep your magma chamber is beneath the crust if you assume the MOGI model applies. You can get some idea of how change in pressure and change in volume inside your magma chamber can affect the observed vertical displacements and horizontal displacements. So we're going to use two equations here. So the vertical displacement U sub Z, that's the amount that the ground goes up above your magma chamber when it fills up and volume and pressure change. It's equal to 3 times the magma chamber radius cubed times delta P, which is the change in pressure inside of the magma chamber as it fills up with new magma. D is the depth to the center of the magma chamber. It's divided by 4 times G. G is the elastic shear modulus or rigidity of the crust surrounding the magma chamber times depth squared plus R squared, which is the radial distance out away from the center of your volcano to where you're actually measuring that displacement to the 1/2 power. So horizontal displacement, U sub R, that's the amount of displacement you can measure as you go radially away from the center of your volcano. It's equal to 3 times the magma chamber radius cubed times the change in pressure inside of that magma reservoir as it's inflating like a balloon, times R, which is the radial distance away that you're actually measuring that displacement signal, divided by 4 times G times D squared plus R squared to the 1/2. Okay, so A is the magma chamber radius, typically 500 to 1,000 meters. That's kind of a typical range that might be reasonable for a magma chamber. Although I have to say, we don't really know what magma chambers actually look like. There's a lot of inferring that goes on and a lot of assuming from things like geophysical signals and petrology. Delta P is pressure change inside of the magma chamber, so typically 10 to 40 megapascals. G is the elastic shear modulus or rigidity of the crust. This is 30 gigapascals, or 3 times 10 to the 10th pascals. That's a big number. So the crust is really stiff, even though we assume that it behaves elastically. D is the depth to the center of the magma chamber. Typically 3 to 10 kilometers in depth is a range you can measure with geodesy. You can have magma chambers that are deeper, and sometimes you can have them that are even a little shallower. R is the radial distance from the point source. So this would be the radial distance away from the volcano where you can still measure these displacement signals. Okay, so the units of U sub Z and U sub R are in meters given the MOGI equations. So you want to pay really, really close attention here when you're doing your homework problem set to unit conversions, because you're going to have to convert from meters to kilometers or vice versa. You're going to have to convert from gigapascals and megapascals to pascals and vice versa. So you need to do a full unit analysis when you're working with these equations for your homework problem set, or you're going to get answers that are orders of magnitude off from what they should be. Okay, so we know that from the ideal gas law, you can basically equate pressure and volume pretty simply and mathematically. So we're going to do that, and I'm not going to go into the details of the math here in order to save your brains from too much video time, but linked into the end of this PowerPoint, we'll go over some slides that show some background, and there is where you'll see how to convert from delta P to delta V in these equations. So the relationship from the MOGI model for surface displacements and volume change is as follows. Same model here where you have a magma reservoir that's buried deep in the crust. It's got a radius of A, depth of D, radial displacement R, or I'm sorry, radial distance away from the center of the volcano is R. U sub Z is vertical displacement and U sub R is radial displacement. So U sub Z in this case, the vertical displacement, uplift or subsidence, is equal to 3 times delta V, which is the volume change. That's the amount of volume change you have in your magma reservoir as it fills up with new magma. D is the depth to the center of the magma reservoir. 4 pi times d squared plus r squared to the 1.5 power. You'll notice you don't have g here anymore. You just have a dimensional volumetric related radial set of constants, 4 pi. Horizontal displacement U sub r is equal to 3 times delta V times r, which is the radial distance away from your volcano that you're making these measurements, divided by 4 pi times d squared plus r squared to the 1.5 power. So the parameters are the same as in the equations for pressure change, but now we're looking at volume change in meters cubed. So remember, you're going to need to pay attention to your units here. Volumes of historical eruptions range from 1 cubic meter to 15 cubic kilometers, sometimes even more. Okay. So for your homework problem set, you're going to be asked to do a couple of things. You're going to be given surface displacement data for uplift across some volcano X, and you're going to use a MOGI point source equation to solve for the change in pressure and depth of the magma chamber. This is a typical sort of application that you might use with geophysical monitoring data, but for this problem set, it's a little simplified. So first, you're going to need to calculate the surface uplift versus radial distance for variable pressure and volume magma sources. And you're going to actually end up calculating a goodness of fit statistics of your model compared to some observed data that you're given next. So to consider goodness of fit, you're going to use a Pearson's chi-squared test. So this is a statistical model that allows you to compare observed data with model data or expected data based upon your model calculations. And chi-squared is given by this equation. The chi-squared parameter is equal to the sum over I observations, your observed displacement minus your model expected displacement squared divided by the expected model value. This gives you basically an understanding of how well your model fits what you observed. And if it doesn't fit very well, then your whole process would be to go back, change the parameters in your model with some reasonable assumptions, and run the statistical model again, and you keep doing this until you converge on a chi-squared that's a minimum value, which indicates that what your model results are saying are accurate for your your observations. And you'll see how we're going to employ this in your homework coming up here. So your first step is you're going to calculate displacements given the equations you've been given for the MOGI model. And you're going to set up a spreadsheet to do this. So you're going to create a spreadsheet that has the given values shown here in these yellow cells. So radial distance in kilometers is going to go from 0 to 30. You're going to be given a shear modulus of 30 gigapascals, a magma chamber radius of half a kilometer, 500 meters, a magma chamber depth of 5 kilometers, and a change in pressure of 10 megapascals. So you can see right here already, you have two different units for pressure. You're going to have to make those synonymous with one another to make the calculations work. Secondly, you're going to make your calculations. You're actually going to retrieve your vertical and horizontal displacements in meters. So shown here, these orange cells, these are where you're going to do your calculations based on the MOGI model equations that are given to you. And you're going to return your answers in meters. So vertical displacement in meters in orange here is one thing you'll calculate. Horizontal displacement in meters here is another thing you're going to calculate. You're going to plot your results, and you're going to get a plot that should look like this. You're going to have horizontal displacements as shown in red here as a function of distance away from the center point of your volcano, which is 0. And you're going to plot your vertical displacements here in meters as a function of distance away from your volcano radially. Okay, so the second step, you're going to be given radial distance and displacement observations, and this is in a spreadsheet that you can download from Blackboard, or if you exit slideshow view in your PowerPoint file, you can double click on this spreadsheet image here and it'll extract it for you in Excel. So you'll be given these data here in yellow, right? Radial distance, vertical displacements that are observed, horizontal displacements that are observed. So this is kind of the reverse of what you did in the prior step. Here you're given the displacements that were observed by GPS data, and you're going to see how close the MOGI model calculations are to these data using chi-squared. All right, so the purpose of this is to try to figure out the depth and source strength of the magma chamber. So that's how deep the magma reservoir is and how much of a pressure and volume change is causing the displacements that you're seeing. So you're going to search for a relationship between pressure change and depth of the magma chamber that requires the calculation of chi-squared goodness of fit. Okay, so to do this, you're going to be given shear modulus data, 30 gigapascals. You're going to be given a magma chamber radius of 1 kilometer. You're going to change the depth and pressure. So you're going to use these two cells to do that, starting with a depth of 5 kilometers, starting with a change in pressure given to you in your homework assignment. You're going to keep changing these. So you'll see here now you've got columns E and F. These are where you're going to make your calculations based on the MOGI model like you did before. So each time you make a change to depth and change in pressure, these numbers are going to change. So what you're going to want to do is, after each iteration, you're going to save the results. So you'll save the results for a certain, depth 1 and change in pressure 1. Then you're going to add depth 2, change in pressure 2, you're going to recalculate it, and then you're going to save those. You want to save all of your calculation data because you're going to want to run the chi-square model for each set of model numbers you've calculated. So note the units. This is really important. I think in my years past of teaching this course, the biggest mistake I've seen students make is that they do not do their unit conversions properly. So you need to remember pressure change is in megapascals and shear modulus is in gigapascals. So pascals are equal to Newton per meter squared or kilogram per second squared meter squared. 1 megapascal is 10 to the 6 pascals, and 1 gigapascal is 10 to the 9th pascals. So you're going to want to make sure that all of these square up with the unit of pascals before you do your calculations. Okay, so after you've started to make your model vertical and horizontal displacements, you're going to do a chi-squared calculation between the observed displacements that are shown in yellow and your calculated displacements shown in orange for each depth and change in pressure. So you'll do this each time. You're going to calculate chi-squared for each radial distance, and then you're going to sum it all up to get a sum of the chi-squared, and then you're going to add these two numbers together to get total chi-squared. So you're going to want to do this one at a time. You're going to hold one parameter fixed while you change the other one, and vice versa. Okay, so here's some background about what you're going to be doing and some references that are relevant to this module. I'm not going to go through this for this video, but you should read this in detail. Here's details on how to convert volume change from pressure change. So you need to go through this before you do your homework assignment so you understand how we're transforming delta V to delta P. And then Here's a big hint for your homework assignment set. When you calculate minimum and total Pearson's chi-squared for the parameters pressure change and magma chamber depth, you're going to want to find the minimum. So for example, if you're holding your pressure change constant at 20 megapascals and you're varying magma chamber depth, for each depth you're going to calculate total chi-squared. Then you're going to change the pressure and you're going to recalculate the best fit models by varying depth. So when you find a minimum, when you're plotting total chi-squared as a function of the depth you're changing for each delta P and magma chamber depth, you'll find a plot that looks like this, where this is total chi-squared as a function of your model depth, and you're going to land on a minimum. So the minimum point on this graph is 5.5 kilometers. It best describes the depth of the magma chamber at 20 megapascals pressure. So I'm giving you a big hint here. You're going to want to converge on an answer that looks something like this. Okay, so first, read this PowerPoint file completely and in detail before you get started. Next, read the Word document that explains your homework assignment before you get started so you know everything that's expected of you and you don't miss points because you forgot to do something. Number 3, review the Mogi model and equations on slides 5 through 8. Number 4, be really careful with units. There are several unit conversions that you'll be required to do in this homework. You're going to need to make sure that megapascals and gigapascals are accounted for relative to pascals. You're going to want to make sure that when you're asked to calculate something in meters or kilometers, you do the correct calculations. If you're getting answers that are off by orders of magnitude, go back and recheck your unit conversions. And if you need help, just ask me. So first, perform the first set of calculations using slide 9 as a reference. You can compare your numbers and graphs to what is shown in slide 9 to see if you're doing your calculations correctly. Again, if you get an answer that's off by orders of magnitude, go back and check your unit conversions. Next, download or extract the spreadsheet that has all of the observed displacement data that you're going to check with the chi-squared model against your model observations or model calculations. So the spreadsheet is linked in slide 10 and it's also available to download in Blackboard in the course materials section. You'll use that spreadsheet to finish the rest of your problem set. All right, good luck and have fun, and let me know if you have any questions.